Now we come to the multiplying and dividing issues that occur with radicals. Mostly what we've got going on is multiplication. The division is not quite phrased in exactly that way. It's actually phrased slightly differently. And we deal only with a little bit of it at this point. Multiplying. We've got regular multiplication that we have used in the past, where the coefficients need to be multiplied together. And then we've got the radical stuff that could show up, which means that we would have to bring in one of our newer rules that said that we can combine square roots together. So the first example reminding us of this rule, we can combine square roots together, and we always need to watch out for simplifying what we have in our answers before we decide that that's our final answer. Well, the square root of 15, we can't break off anything that has a nice square root, so we get to leave that. In the second example, where we have coefficients, we put those coefficients together. We put our square roots together according to our earlier rule. And in this particular case, the square root that we have can be simplified in order to get a little bit further along before we have our final answer of negative 48. The other thing about multiplying, though, is that any of our fancier problems, like the one that you see showing up here that we'll do in a moment, are going to be done using the kind of multiplication techniques that we've used in the past when we were talking before about polynomials and carrying that along to some of our other topics. So we distribute when it's appropriate, we FOIL when it's appropriate, and well, that pretty much takes care of most of what we would have to worry about. It's just that we've got those square roots that could also show up. So in this next example here, out in front of our set of parentheses, we officially have only one term. So this would be a case of distributing, and let's use a little bit of color here to emphasize that we've got that 5 square root of 5 out in front that needs to be distributed to the 2 square root of 5 at the beginning of our set of parentheses. And we've got that 5 square root of 5 appearing out in front that would need to be distributed to the 2 at the back end of the parentheses. Well, looking at these as 2 separate multiplication problems, we have the 5 square root of 5 times 2 square root of 5. So that would mean that we have 5 times 2, and we would have the square root of 5 times the square root of 5. And that would give us 10 square root of 25. I'll tell you what, let's actually write that one off to the side here. 10 square root of 25. Square root of 25 would give us a 5. And so for part of our answer, we would be looking at possibly a 50 appearing. In the other part of our answer, we have the normal 5 times the normal 2 to worry about, meaning that we would have a 10 square root of 5 showing up there. And putting that together with the 50, and thinking back to our comments about adding and subtracting. The 50 does not have a square root, let alone a square root of 5, meaning that these are not like terms and cannot be put together. Therefore, this would be our final answer. And we have that same sort of idea in mind as well, possibly based on how much we remember about our distributing in the first place. Usually with our distributing problems, we are not likely to see a lot of extra or any extra combining like terms, just because of the nature of how those problems are created for us, unless they are longer and more complicated problems that involve not just distributing, but also some extra adding and subtracting and maybe even more distributing to worry about as well. But for a basic distributing problem, we do our distributing, we simplify each of those terms, and yeah, we're usually just good to go there. We can also use those same sorts of friendly comments about FOIL. So, with a problem like this, one term, two terms, one term, two terms. So we've got a binomial times a binomial. Yes, those square roots appearing, but we have a binomial times a binomial. And when we talked about those before, we said FOIL. F for first, meaning that we would have our x square root of y times 3x square root of y. Our O, meaning that we would have our x square root of y times our negative 2y. I, where we would have our y times our 3x square root of y. And last, our L, where we would have y times our negative 2y. And we said that as part of our first step of FOIL, we would always begin by having addition in between all of those pieces. Then we start looking at these. We would have 4 separate smaller multiplication problems to work out. So we would have a normal x, a normal 3x that we could put together to give us 3x squared. We would have the square root of y times the square root of y that we could put together as the square root of y squared, and immediately realize that that could be unlocked so that we had, I'm going to write that a little bit neater, 3x squared times a normal y. Square root and power of 2 unlock each other. The O part would end up being a negative, and when we put things together in a more normal, traditional fashion, that means that we would have the 2xy, and at the very end, the square root of y. And then our I would remain a plus, but rearranging things into a more normal sort of appearance would mean 3xy, square root of y. Hey, wait a minute. Those two sound alike, and if I take a closer look at them, they do in fact both have an xy and a square root of y. So I can go ahead and combine like terms so that we would have a 1 xy square root of y showing up from that. Something that we also expect to see a great many times as part of FOIL, because as in the past, the O and the I parts very often do end up being like terms. The L at the very end, which ends up being a minus. And since there are no square roots, that behaves in exactly the same way that we're accustomed to. So that final answer there, 3x squared y plus xy square root y minus 2y squared. We're welcome, as in the past, to continue to use FOIL whenever we can, but we do have those rules that we've mentioned in the past, not just as rules for multiplying, but slightly different arrangement gives us rules for factoring as well. One of these is particularly helpful, and it's this third one, the one that we've seen before that connects to the difference of squares factoring formula. And this is special because of that whole arrangement in these factors. the first term and the second term are the same, one factor has a plus, one factor has a minus. Because they're special and special things get names, we end up calling this conjugates. These two numbers, square root of 5 plus 3 versus the square root of 5 minus 3. They're conjugates. It's kind of like saying they're fraternal twins. And when we multiply conjugates together, there's something that ends up happening. Again, you're welcome to use FOIL, but just to use that multiplication formula because it's a little bit quicker for us and gives us the opportunity to make another useful comment, we're going to do it that way. The first term is a square root of 5. I would want to square that according to my formula. The second term that shows up is a 3, and I would want to square that according to my formula. And in the middle of those two things, I would want to put a minus sign according to my formula. Now, if I literally go through the process of doing the square root of 5 times the square root of 5, and I get the square root of 25, which would simplify to be the number 5, hey, wait a minute. If all I'm going to end up doing is get a 5 out of that, it certainly looks like the square root and the power of 2 unlock each other, even though they're in slightly different positions with relation to one another. Instead of that square root being outside and the 2 being a power underneath, the square root now is inside a set of parentheses and the 2 is outside. And yet that square root and power of 2 still unlock each other. They sure do. They sure do. So that's a nice comment to be able to make that might be helpful in certain other kinds of problems that we see in the near and far future. But the other important thing to notice here is that we end up getting an answer free of square roots. There were 2 square roots in this original problem that showed up, and our answer doesn't have any. In fact, because there are no crazy variables going on, we literally just get a nice, friendly number. That's very noteworthy and very possibly helpful to us in the future. Not the immediate future, but when we get into, farther along in the future, when we get back into division with these radical expressions, this conjugate business, not having any square roots in the answer, ends up being a very helpful note worth making and worth remembering. The other example here, notice also, is multiplying conjugates. So according to our formula, we would take the first term and we would square that. And we would take the second term and we would square that. And we'd put a minus in the middle. And if I take the 1 and square it, and I take the 2 and square it, and I take the square root and square it, and I take the 2 and square it, and I take the 5 and square it, and take the square root and square it, I again end up with an answer, not quite as nice and friendly looking, but still noteworthy in that there are no square roots that appear in this answer. So I have managed to have a problem now that had 1, 2, 3, 4 square roots appearing in it, giving me an answer without any. Noteworthy, helpful, farther along in the future. But these are noteworthy for that very reason, so that when you see this idea again, when you come back to dividing with these radicals, you can say, ah, yes. Now the deal as far as dividing, again, we're not really officially calling it dividing. What we're really looking at is just a really a tweak on simplifying certain kinds of problems. We had that rule from earlier that said we really don't like square roots in the denominator. And if we don't like square roots in the denominator, then there are two different things that could happen. We could have a nice square root in the denominator. We could have a not so nice square root in the denominator. Well, if you have a nice square root in the denominator, great. Easy peasy lemon squeezy. If we do not have a nice square root in the denominator, what on earth can we do? We rationalize the denominator. We're going to do a little tweaking with things so that we can transform that denominator into what we would want it to be, something that doesn't have a square root in it anymore. I'm going to pull in an old tool from way back with dealing with fractions and rational expressions. If I need to tweak something on the denominator, then I'm going to do that same sort of tweak up on top, namely if I am going to multiply on the denominator, I'm going to multiply by the same thing on the numerator. And if I pick just the right thing in these kinds of problems, I can make those square roots unlock and go away. Square root of 3 showing up in this first example down in the denominator, that doesn't have a nice answer. In order for me to create a nice answer, I would need the number 4. Can't get that quickly. I would need the number 9. Hey, wait, I can get that quickly as long as I put in another square root of 3. Multiplying those two together would end up giving me that square root of 9. But if I do it to the bottom, I'm going to do it to the top. So got that emphasized there with green. That ends up getting me my denominator that no longer has a square root in it. And before I move on, I even look at the fraction, normal 7 on top, normal 3 on the bottom. Can't do any sort of reducing there. So this actually is good to go as far as new rules and old rules. Same sort of idea, and we actually don't have anything more complicated for right now than this. Rationalizing the denominator where we only have a monomial denominator. That's as bad as it's going to get for the time being. In the future, things get a little bit more involved, then we'll revisit the topic. So I can start in this particular case by recognizing that, first of all, we do not like to have fractions underneath our square root. And so let us start with breaking this apart. And then making another observation that we do not like the denominator there having those two separate pieces because, hey, that square root of 36, if it was by itself, would actually be rather nice. So we can break things apart further and take care of that square root of 36. But that does leave me with the issue of having the square root of x still in the bottom. And it's that square root of x that's still jamming us up here because we are not supposed to have a square root in our denominator. The only way that we would be able to get rid of that square root is if we find something that we can introduce. So it's going to have to be something with a square root on it that would eventually get us an x with a power of 2. Well, if we just had one more extra x down there in the denominator underneath the square root, then we would get the power of 2 that we're looking for. And if I do that to the bottom, I have to do the same thing up on the top, meaning that we would have our numerator square root of 13x. And because we have designed our denominator, we know what it's supposed to turn out to be. The 6 that's already nice and normal and there to begin with, and the square root stuff that's supposed to combine together and not have a square root anymore. The square root and the power of 2 will unlock each other so that the denominator will end with just a nice normal x, no more square root down there. I've got something that's good to go. I don't have anything nice up on top that might work with the 6, so there's no normal type of reducing that I can work out there, which means that this is as far as I would take that answer. Again, for right now, these examples up at the top here, these both have denominators that are monomials. If we have a more complicated denominator than just a single term showing up, then we would still have the same basic goal, get rid of the square roots, but we would have to have a different sort of process, at least slightly different, in order to accomplish that goal for the future. For right now, rationalizing the denominator, these are the kinds of division style problems that we would have to deal with that none of our earlier comments or procedures would have helped us with. So we have the little extra comments here that allow us to take care of that, and that takes care of everything that we might need to do for the time being with radicals.